This is my Framebuilding frame welding fixture. I designed and built this in my shop a couple years ago, and yeah, I mean, it just holds all the different pieces of the bike frame when you weld them together into one piece. It's adjustable, it's got different interchangeable parts. I did a video already talking about the overview. I want to go a little bit more into the design specifics and the strengths and the weaknesses of different parts of the fixture, why I chose to do things certain ways, and how I maybe do things differently this time. If you're going to build and design your own frame fixture, it's useful to think about this kind of stuff on the way in, or if you're just going to buy something from the options that are out there, really useful to have this sort of thoughts in your head so you can make a more educated decision. Let's get into it. So if you use BikeCAD, it gives you 5 variables that you can use to set up this fixture. You take those 5 variables and you can adjust. First of all, there's this is XY00 on your coordinate plane. If this is the x-axis and this is the y-axis, from here you have an x coordinate, and up to here you have a y coordinate for the bottom center of your head tube back to the bottom bracket shell. So if you want to adjust the x-axis, you got to loosen all 4 of these guys, and you slide this. It's kind of tight. I didn't want it to be sloppy, but it's kind of tight to make an adjustment. And you can read off of a scale here. There's a pointer that references a scale, and that's in millimeters. That's how you adjust the X. You adjust the Y a little bit more easily. It slides up and down here. And there's a millimeter scale and a ruler reference there. We have the same thing on the rear end of the bike. You have an X adjustment. You got to loosen all 4 of these handles. And now I can slide this forward and backward. And it's a little bit cumbersome. You know, I wanted it to fit tight, but I didn't get it perfect, so it's a little bit too snug, and it's kind of a pain to slide. For the y-axis, you loosen both of these, and you slide this up and down, and you can reference the rule here. It's all built in. So then the 5th adjustment is where you set the seat tube angle relative to the head tube angle. So a lot of fixtures, the head tube angle is actually your head tube angle against the ground, and then your seat tube angle is your seat tube angle against the ground. And I did a wacky design with this fixture. I'm not sure it's really better or anything, but it's different, and it's where it's the seat tube angle minus the head tube angle, and that gives you the difference, which is what this scale reads. So if you have like a traditional road bike that has 73-degree parallel seat tube and head tube angle, right, you would set this to 0, and then you would lock it in. Or if you had like more of like a modern hardtail mountain bike and you had a 74-degree seat tube angle, and then you have like a 68-degree head tube angle, that's like 6 degrees of difference, right? And so you can imagine the seat tube is steeper relative to the slack head tube, so you know that this needs to go forward. And I said 6 degrees. And so now what happens is, you really want to have your design finalized. With this style fixture, you want to have your design finalized before you go setting up the fixture, because if you were to change the head tube angle or the seat tube angle, what it would do is it would change these coordinate positions in space. And so my thinking is, design is something that you do before you fabricate, right? You want to design and get the design where it should be based on your inputs, based on your knowns. You don't want to go back and forth between fabrication and design generally. That was my thinking, and so I made a fixture where you do all the design ahead of time and then you just build it. And so you set this angle and then you do all these things. I think in practice sometimes you would maybe find that you wanted to tweak these just a little bit to make your tubes fit better or something, and it might be nice to be able to independently adjust those angles. So I'm not sure that I would do that over again. But anyway, that's how the fixture basically works. So there's a couple interchangeable parts in here that allow you to do a variety of different things. Up here on the front we have this lower head tube puck, and I like to have, you know, a tapered cone on the top, because this is not an important dimension. Like where this ends up doesn't really matter, it's just to hold it in place. But the bottom of this bottom flat edge, that sets the Y coordinate position for your head tube. And so you really want a hard stop. If you did a taper on the bottom and a taper on the top, then it would depend on what head tube material you used, how far it sat down the taper. And to some degree, it would depend how heavy your chamfer was, right? On the inside of that tube, if you have a heavier chamfer, your tube's gonna sit lower. And you know, that's more of a fussy thing, but I just want this to be, I think this is 30 millimeters from top to bottom, and that's built into this rule. It's calibrated so that I can read this thing direct and I don't have to do a conversion. That number that I'm reading right there is actually the height of this, the bottom shelf of this head tube cone. So that means that if I want to work with different size head tubes, I need different, you know, pucks or whatever you call these. And so I have those. You just loosen this M8 screw, and there's a little step here, and that's to help me get a good location on this. If you didn't have that step and it was just the screw, you would need a little bit of clearance for the screw and it would be a little bit sloppier. So I tried to make a nice tight fit, and it's pretty tight. You can barely feel any sort of slop side to side here. There's not really a perceptible wiggle, and I think that's 19 millimeter or something. And now I switch into this larger diameter. So that's for a 34 millimeter headset. This is for a 44 millimeter headset. And you can make these in all different shapes and sizes. And again, it's a nice tight fit, and you just run the screw in. It's got this press to connect fitting on it, so that if you wanted to back purge your frame with argon, you just push the hose onto here, and now argon can flow up through this hole to the inside of your frame. I also have one up here. I don't know if you would need these on both ends of the head tube, but I have them. It's an option. I have it on the seat tube here. I have one on the bottom bracket. So they're in all these different places. So, you know, for the bottom of the head tube, you have this hard stop, and I need to make all these different sizes for all the different kinds of head tubes I'm going to use, because you want the inside diameter of the head tube to be hugged tight against this. For the top of the seat tube and for the top of the head tube, these tapered cones should be acceptable for everything. Down here on the bottom bracket shell, my thinking was I didn't want to design some elaborate system with interchangeable parts for different widths of bottom bracket shells. And so this standoff here for the bottom bracket shell is a one-size-fits-all solution. It's great for my one-off fixture because it made it easier for me to design and build it. If I was going to make a bunch of these and sell something like this, it'd be kind of a pain in the butt, because this is a big chunk of material. It ends up being kind of expensive to have all different specific use standoffs for the bottom bracket shell. So the way it works is, you know, this is 68 millimeter bottom bracket shell, and if I want to switch to a 73 millimeter bottom bracket shell for like a mountain bike standard, you would need this to be a shorter post so that it stays centered, right? The center line of the frame should lie in here as a factor of, you know, where you set all the pieces. It should already be pretty much centered, and so you need this to be shorter in order for a wider bottom bracket shell to still be centered along the center line of this. And so the way that works, I just reach my wrench around the back here, and so this is sort of how it works. Again, I have this step that fits pretty tight on there, so there's not a lot of slop for it to move around. And then I have this screw and this special plug washer thing I made. And so if I wanted to do a bike with a different bottom bracket standard, I'd just turn a different piece of this on the lathe. And yeah, I mean, that's not really the best system, but it was simple for me. Most of the bikes that I was making when I designed this were for 68 millimeter English thread bottom bracket shell, and that's what this is designed for. It's also, you know, it's back purged, and it's pretty easy to swap these. I can do it and put it all back together again really pretty quickly. If I was going to make and sell a tool like this, I would want to come up with a more elegant solution where most of this material of this standoff was, you know, like, it would stay on the fixture, and then you would have a smaller piece near the end that was interchangeable, and that would account for different diameters and different styles of bottom bracket shell and different widths. And so I think that's how I would do it if I was going to make a batch of these. So I want to make a point about some of the motion. There's a lot of linear motion in something like this. You want things to be able to slide back and forth in just like one axis. You want to isolate the axes so that as I slide this whole assembly forward and back, it stays essentially perpendicular to this main extrusion. And so the way that I tried to do that, So the way that I tried to facilitate that linear motion was with plastic guide keys that are made out of Delrin plastic, and they slide in these grooves. So I can pull this whole thing out and show you. So yeah, these are the plastic guide keys. These slide in the channels of the extrusion, and they fit in there pretty snug. And then these here are long T-nuts, right? They have this profile that can sit down inside of the T-slot, and then they can be drawn tight with the screws. These little screw handles are nice. They have a spring inside of them, and when you pull back on this, now this part can kind of freewheel in there. So you can adjust the angle of this if it's in the wrong spot. So anyway, that's how I got the linear motion. That's how I got them so that they could slide in one axis over their length without changing the angles and without, you know, having a sloppy fit. And the idea was that the plastic would slide nice and smooth against the rest of it. It kind of works. I'm not totally happy with it. So, you know, if I was going to redesign this and build this over again, I would try and find something a little bit more elegant, but it works. If you're building your own fixture, you could try something like this. A similar approach that I've seen people do is they'll use dowel pins. So, you know, if this is supposed to have something like a 10mm nominal slot width, you'd have to take measurements and see exactly what size it is. You wouldn't want it to bind up, but you could drill precision holes in your base plate, and then you could press in a pin, and you could use those pins to keep it from twisting or sliding up and down, so that you just want to isolate the motion into just one axis of motion. And there's actually, when I made this, I wasn't aware of how many off-the-shelf options there are for linear motion that exist if you're going to build your own, you know, CNC router or something. There's lots of like cheap linear motion components, and those might be a good place to look for if you're trying to build your own sort of thing. So on the rear end of the bike here, you have dummy axles, and depending on what kind of hub standard you use and what style of dropouts, you have different widths to these dummy axles, and then they have actually like different sort of mating features in there. And then these screws and washers are used to clamp the dropouts onto the dummy axles. So these are made by Anvil Bike Works, and Don provides a really super valuable service by not only making great tools and fixtures and doing so for the last 20 years, but also he has so many different styles of these ready to ship at a moment's notice. They're really, you know, reasonably priced. So many people build their own tools and fixtures based around these. So I had bought some of Don's disc brake tab welding and, you know, fit up fixtures, and then I had a selection of these around already, and when I made my frame fixture I used these, and yeah, it's just really cool that he has so many of these available. And you know, if you're going to build your own thing, it makes sense, really honestly, to just buy the ones that Don sells because they're so cheap and readily available. If you have you know, a rotary table or a machine with like a fourth axis or something or whatever, you know, you can make these yourself, but there's really a lot of work and screwing around involved in these, and they're like $35 or maybe a little bit more each. They're really not that bad for how much of a pain it would be to make these yourself. So anyway, the way these go into the fixture is, you know, you load them from below, and I used a ball end mill, and I made this half round slot. They get loaded in from below, and then there's a real simple clamp here, and that holds them in place. Now I had a way cooler and more slick of a clamp. Had like a spring in it, and it had guide key, and all this cool stuff. It was very one-handed, and you weren't going to drop anything on the floor. And I realized it was actually in the way. When you go to remove the frame, it gets in the way, and it's no good, right? And so it doesn't matter how cool it is if it doesn't work. And so what you get into is that you can imagine the frame goes in individual pieces. And now you weld it up, and now it's one piece, essentially. And you go to remove it, and you got to be able to get it out of there. And I thought about that, and I was aware that this sort of thing can bite you in the ass, and I still didn't realize that what happens is, in order to get it out, the dropout doesn't come straight down, it kind of pivots back. So this is your center of rotation as you're trying to get the frame out of there. You got to lift up the front end enough to get off of this little puck here. Well, I mean, you know, you can release this and slide it down out of the way, but you don't want to have to do that because then you lose your adjustment. You know, if you were going to put the frame back in, which a lot of times you would do for, you know, maybe you do the front end of the frame and you weld it out of the fixture and you put it back in and then you add on the rear end. Anyway, you don't want to have to move this stuff and change your adjustment. And so here, when you go to get the frame out, it kind of pivots around this point, and your dropout really comes back down on an arc this way, or your dummy axle does. And so my clamp mechanism was like right down here, and you would slide it back out of the way and it would go straight down, but it was in the way for clearing. So I had to make a clamp that was a lower profile that I could get out of the way more easily. And that's what this is. And so I also had to come in here and I had to machine some extra material away so that as it's swinging back, it can clear. And so this seemed like a good idea, but in practice, I was finding that it actually, it wasn't perfect. So here's another part of the fixture. I'll show you how this comes apart. These are I call these the standoffs. So the lower head tube standoff, upper head tube standoff. This one here would be the upper C tube standoff. And these are kind of similar principles to these plates that I did on the front and the rear, where there's a Delrin plastic guide key that keeps them so they can only really slide in one axis at a time. If I loosen this, I can slide it up and down, but it can't really twist around and it can't slide forward and backward. It's just isolated to that one axis of motion. So if I pull off this little cap, and if I loosen this up, I can slide it at the top, and you can kind of see what I'm talking about. There's this long T-nut, and this T-nut just fits in the slot there, and it allows me to tighten up against the slot, up against the extrusion. There we go. And so now, I have a screw that runs all the way through here on this handle, and I can tighten up against there. And you can see that the plastic guide keys just kind of keep it so that the whole thing has like one axis of adjustment, right? That's what you want to do. You want to isolate the motion. And then it's got a pretty broad contact here along these faces so that hopefully it always sits square. You don't want it to you don't want it to be moving around on there. You want it to have nice broad contact. It'd be good to get this anodized so that it had that skin of like tougher aluminum. This is just soft unanodized aluminum. If you were to get this whole thing anodized and plated, especially if you got it type 3 hard anodized, it would be tougher and more wear resistant. Like this surface here that's black, that's anodized. And it's not just cosmetic. It makes the surface tougher and stronger. And depending on the process, if it's type 2, it makes it a little bit more wear resistant and harder. It keeps the aluminum from wanting to gall against other materials. If it's type 3 hard anodized, it's really hard. The surface is very hard. And so for something like this where it's sliding against itself, you'd really like to see that type 3 hard anodized. Would be awesome. It would give you a lot of service life out of the parts before they would wear out. And you wouldn't get this sort of like you can see the aluminum is sort of smearing from this piece into the anodized one. It's kind of leaving a mark there, and that's a sign of it kind of wearing away. It just doesn't slide as smooth as it could. But that's the way that I facilitated that. Is I machined a notch in here, and then I put this guide key down in, and so they're sort of mated together, and that's an anti-rotation feature that allows these to slide pretty nicely against each other. One of the tricks with this was that I decided to do this heavy piece, and I have something like a 7 or 8 inch long screw that runs all the way through here from this handle all the way back, and you have to drill a hole all the way through there, and deep drilling kind of sucks, if you're doing it on a manual machine or a CNC or whatever. I think what I did was I drilled halfway in from either end, and you got to get the holes to line up, and it's not that hard if you're doing a batch of them and you had all the right tooling, but it's just kind of a pain in the smaller volumes. It's a consideration. Some people will design these so that the screw that clamps is only like an inch or so long, and you have more of an L shape to this piece, and so the screw only has to travel through a little bit of material, and then what extends here is like thinner, and so you'd have your handle way back up here instead of on the end. You wouldn't need to do that deep drilling. You wouldn't need such a long screw. It's just all different ways to design it, and that's another consideration. I've reflected a lot about what was good and bad, and I just wanted to share some of that. Some of those thoughts that might help you get the most out of your design or purchasing situation that you might be in. Hit that subscribe button, and I'll see you on the next video where we talk about all sorts of frame building related stuff. See you there.